In digital circuits, a logic level is one of a finite number of states that a digital signal can have. Logic levels are usually represented by the voltage difference between the signal and ground, although other standards exist. The range of voltage levels that represents each state depends on the logic family being used. Two-level logic. In binary logic, the two levels are logical high and logical low, which generally correspond to a binary 1 and 0 respectively. Signals with one of these two levels can be used in Boolean logic for digital circuit design or analysis. Active state equals, the use of either the higher or the lower voltage level to represent either logic state is arbitrary. The two options are active high and active low. Active high and active low states can be mixed at will. For example, a read-only memory integrated circuit may have a chip select signal that is active low, but the data and address bits are conventionally active high. Occasionally a logic design is simplified by inverting the choice of active level. Plus binary signal representations, the name of an active low signal is written with a bar above it to distinguish it from an active high signal. For example, the name Q, read Q bar, or Q naught, represents an active low signal. The conventions commonly used are, a bar above, a leading slash, a leading lowercase n, a trailing, or, and b suffix. The slash convention is also used with signals that have a meaning in both states. For example, it is common to have a read-write line written a slash, w, indicating that the signal is high in case of a read and low in case of a write. Many control signals in electronics are active low signals. Logic families such as TTL can sink more current than they can source, so fan-out and noise immunity increase. It also allows for wide OR logic if the logic gates are open collector open drain with a pull-up resistor. Examples of this are the ES2C bus and the controller area network, and the PCI local bus. RS-232 signaling, as used on some serial ports, uses active low signals. Logic voltage levels equals, the two logical states are usually represented by two different voltages, but current is used in some logic families. A threshold is designed for each logic family. When below that threshold, the signal is low, when above high. Intermediate levels are undefined and the behavior of the connected circuits is highly implementation specific. The problem of the circuit designer is to avoid circumstances that produce intermediate levels, so that the circuit behaves predictably. Nearly all digital circuits use a consistent logic level for all internal signals. That level, however, varies from one system to another. Interconnecting any two logic families often required special techniques such as additional pull-up resistors or purpose-built interface circuits known as level shifters. A level shifter connects one digital circuit that uses one logic level to another digital circuit that uses another logic level. Often two level shifters are used, one at each system. A line driver converts from internal logic levels to standard interface line levels. A line receiver converts from interface levels to internal voltage levels. For example, TTL levels are different from those of CMOS. Generally a TTL output does not rise high enough to be reliably recognized as a logic 1 by a CMOS input, especially if it is only connected to a high input impedance CMOS input that does not source significant current. This problem was solved by the invention of the 74HCT family of devices that uses CMOS technology but TTL input logic levels. These devices only work with a 5V power supply. Three-level logic. In three-state logic, an output device can also be high impedance. This is not a logic level, but means that the output is not controlling the state of the connected circuit. Four-level logic. Nine-level logic. See also, digital current loop interface, digital signal, line level. References. External links, positive logic and negative logic, simple MOSFET-based logic level conversion or level shift based on work done by Herman Schutt at Philips Semiconductor Systems Laboratory in Eindhoven, level shifter, power reduction techniques and its applications.